So we talked about electromagnetic waves in dielectrics, but waves can propagate in conductors as well. So okay, so here the problem is the following. There is a J vector. This is not vacuum anymore. In many ways, the dielectric case, it still looked like vacuum because you had epsilon and mu, and you could pull that out, and there were no free charges. But that's no longer true because you have Ohm's law. The free charge depends on the electric field. Now, we have to be careful when we do this. In this chapter, and for 2 chapters now, electric fields are time dependent. So if the electric fields oscillate very quickly, the currents cannot reverse back and forth that quickly. So at some point, we'll have to have a discussion of how fast the electric fields can oscillate for this to be a reasonable approximation. Okay, so let me write out again. Every day we begin with what? It's rho free instead of total rho. So instead of epsilon naught, it is epsilon. Because this is really divergence of divergence of D. Divergence of D is rho free. But D is nothing more than epsilon times E. Okay? The Faraday's law does not change. And the magnetic field, still no monopole today. So this is supposed to be H. It's D and H. H is B over mu. So instead of writing B over mu over here, I'm going to take mu and multiply it on that side. So you will have these 2 terms, mu times epsilon dE dt. Normally it would just be epsilon, but now mu times epsilon. And also mu times, let me do it this way because I don't want to waste time, but this really comes from, what should be here is actually, except we're using Ohm's law. Okay, let's talk about the continuity equation, and this has an incredible continuity equation. So free charges are also conserved. I mean, not just induced charges, but free charges are conserved as well. So that means what is this? D rho free dt plus divergence of J free is equal to 0. And so then I have D rho free dt equals, I'm going to bring it to the other side. Yeah? And I'm going to have this as what? First of all, I get a minus, and instead of J free, I'm going to write this as divergence of sigma times E. And then I get a very simple differential equation that has incredible meaning. I'm going to bring the sigma out. Divergence of E is rho free over epsilon. This is a very simple equation to solve. You can verify that rho, and there may be spatial dependence, I don't care about the spatial dependence. It is some initial value, e to the minus sigma over epsilon t. Because when you take the time derivative, the minus sigma over epsilon simply comes out. So define, and I'm going to write this differently, because it brings a characteristic time into the conversation, minus t over tau, where obviously what is tau? So in the electrostatic case, what happens to all the charges? It runs to the surface. Here too, that has to happen, because inside the conductor, the charge density is exponentially decaying. So while it's not zero, it goes to zero pretty fast. There's a condition that the oscillation time here is much less than this guy. No, much bigger. So electric fields are changing at a much bigger rate than this guy. Yeah? I can give you a little more, a better estimation. I know it's crude, but look at this. This is T. And this is what's called the, if I can spell it, is that correct? Characteristic time. Close enough? I'm recording it, so CHARACTERISTIC. Oh, okay. Well, good. So for this to apply, here I have T over tau, yeah? And that should be much less than omega t, because electric fields oscillate, with some frequency omega. Now mind you, we have considered only plane waves. In general, an electromagnetic wave is made up of many omegas. So you get like a Fourier spectrum, so to speak. But all of those omegas have to sort of satisfy this general condition, which then translates to tau is less than 1 over omega. If this is not the case, well, we have to look at other ways of doing this. Probably not so easy analytically, you have to do it numerically. So provided the electric fields don't oscillate too fast, so let me also make this very clear. This is 2 pi times t over 2 pi. So the characteristic time is less than the period of oscillation of period divided by 2 pi of the electromagnetic wave. Then this result applies, and the current, the free charge, not the current, the free charge just exponentially goes to 0. There's a nice constant, I think it's a skin depth. That measures skin depth, and this is D. So say you have a conducting material on one side, it is the distance by which the charge reduces to a factor of 1 over E. And let me make sure I have it right. It's going to, oh, did they use? No, we're not there yet, sorry. Sorry. Okay, so now we know how charges behave. They go to zero. Now let's get back to Maxwell's equations. What are Maxwell's equations again? I erased all of that. I should just leave it. Divergence of E. It used to be rho free over epsilon naught, but we don't care about the transient behavior. We're going to wait till the charges go to zero. So I'm going to do this and call this the steady state behavior. And so what is steady state as opposed to transient? Yeah? So you wait for the free charges to go because we want to get a wave equation out of this. Of course, divergence of E equals negative dB dt. And it doesn't hurt to write this on a regular basis. B equals mu sigma, I think dE dt, rho may go to zero, but J doesn't go to zero because if there is E, there's going to be J. So I have plus mu sigma. Let me leave that there. And again, there's a moral to the story. We get a nice result. You know, you've probably heard of a Faraday cage, where if you wrap yourself in a conducting surface, the conducting surface will just take all the charges away, and inside you'll be shielded from the electric field. That's exactly what's going to happen. The electric field will be shielded, and the magnetic field. And while you get a wave, it sort of attenuates to zero. I mean, exponentially goes to zero. It doesn't go to zero for finite distance, but it's practically zero very quickly. And how fast does it go to zero? That is skin depth. Okay, and we'll get to that. But the remarkable feature is this satisfies a wave equation. Previously, we didn't have this. How do I get a wave equation? Well, I take the curl twice. So curl of E, if you look at the inside cover, I normally wouldn't remember this, but since I was making my notes, I do remember the expression. That's what it is. From the inside cover, you just put E in, and that's what you would get. Fine, but this guy is zero. So I would get a negative Laplacian of, when I write this, I'm taking the Laplacian of each component of E, of the X component, Y component, and the Z component. Okay? Now, on the other hand, this is equal to the curl of negative dB dt. Why? Because if I take curl here, I'm taking the curl there. Partial derivatives commute, so I can do negative dt of curl of B, and that is negative dt. And then I write out the last of Maxwell's equations, mu sigma dE dt plus, oh, there's somewhere a mistake. This is mu epsilon, isn't it? Sigma comes from the J. Yep, mu epsilon. Plus mu sigma E. So then I get del squared minus del squared E is equal to minus mu sigma. Hey, listen, I have minus on both the sides. I'm going to get rid of that. Second derivative of E plus mu sigma dE dt. That is my new wave equation. If I play the same game for B, I get exactly the same with B, but just to have it in the notes, I'm going to write this. Del squared B is equal to mu sigma dB dt squared plus mu epsilon and mu sigma dB dt. Now, if sigma was equal to 0, this is a beautiful wave equation. That was the old wave equation. But here sigma is not equal to 0, but they do still give a wave equation, but it has a different interesting feature to it. I think we have used up the need for this equation. That's Maxwell's equations. Remember, again, we're looking for steady state behavior. Huh? By the way, any questions? Okay, so this is what we'll do. We expect some sort of a wave-like equation, so we play the same game. E to the I kz minus omega t, and you try this, it won't quite work. It will, but then you realize it'll work only if k is a complex number. But thankfully it's been tried before, and we know ahead of time it's going to be a complex number, so I'm going to just put this in there. And then see what happens. And of course, B this is for a wave that is moving in the z direction. Let's take derivatives and see what happens. I have two spatial derivatives, which means second derivative in z. That means I k tilde is going to come out twice. And then I'm going to get the same function. So I k tilde times I k tilde is what? Minus, I squared is minus.
But then doesn't the k tilde have its own?
Well, it may not be purely complex. Minus k tilde squared equal to mu epsilon. I'm taking two time derivatives. What do I get? Minus and minus cancels. Again, I'm going to get a minus omega squared. Then I have a mu sigma. I have only one time derivative. I'm going to get a minus I omega. You might say, well, what has this got to do with that? Well, I get this. If I take this equation, put this in, I get this equation. Because whenever you take the derivatives in the exponential, whatever the coefficient, that just comes out and you get the same remaining function. This can only be true when this goes to 0, because this never goes to 0. So then I get, obviously, or k tilde squared equals mu epsilon omega squared minus plus I mu sigma omega. And then you see, let me make sure my mu, yep. And you'll get, again, exactly the same condition for the B part. Because, I mean, the equation is virtually identical. Now we're done with this non-wave equation as well. So it's weird. You get a wave number or wave vector that is complex. And it's not just purely complex, it has a real part and it has a complex part. And the original solution was this. Yeah? So I have to find the square root of this. So that means k tilde, well, let me write out the expressions. You can check to see that this is the answer. It is not difficult to carry this algebra. But once you know the answer, it's easy to verify. Actually, I would like, because we don't work with complex numbers very often, I would like for you to think how this can be derived. But first, you just see if it works. How do you see if it works? Take this complex number and multiply by itself. What should you get? That number. So this is the real part. I'm going to call this k. This is the real part. So we'll call that k. And this is a complex part. Gosh. We have k, we have k tilde, so we'll call this kappa. Now you have to keep my handwriting straight. So k tilde is k plus I kappa. And so, what will E look like? E, for example, will look like that E is equal to, of course, the complex part, and then I have E to the, I'll explain, E to the I, kz minus omega t. So this k is kept over here because of this. Then I have an I kappa. I have an I here. I times I is what? Minus 1. So it becomes minus kz. So this is an oscillating wave. This is something that attenuates. It exponentially goes to 0, and I get the same thing. And this is, of course, what is skin depth. E to the I, kz minus omega. Skin depth. is nothing but 1 over kappa. So if you go 1 skin depth into the conductor, the electric field has attenuated by 1 over E. If you go 2 skin depths, it has attenuated by 1 over E squared, and so on and so forth. So it's a measure of how fast the electromagnetic field, the signals, would attenuate. And you can look up the skin depth for various different kinds of materials, and I urge you to look at some of them. Look at lead in particular. What do you think the skin depth of lead is? It's going to be a very small number. That's why Superman can't see through lead. And that's why if you're getting your MRI or CT scan, the physician's assistant is always wearing or hiding behind a lead, covered surface. And this doesn't quite give you the relationship between E0 and B0. It's the same kind of relationship that we have applies. So from Faraday's equations, from del cross E equals minus dB dt, you compare this and this. It is easily shown that if you have E to be of this type, the usual complex, e to the minus kappa z, e to the I kz minus omega t in the x hat direction, then B, just like before, it's going to have the y hat direction, e to the I kz minus omega t, e to the minus kappa z. I think I've been fairly good with keeping these two separate. Now, just like the other case, it is hold on, I just need to make sure. It's, yep. No, it is K tilde. Previously, we just had K over omega. Now it's going to just end up being K tilde over omega. Yeah? I would like for you to verify this. Meaning, if you put this expression here and put this expression here, and you pick this to be the E, you'll get this to be the Y. If this is E, then that's B. And everything else, any questions, by the way?
Next to the B term, next to the E naught, so what's that little?
Yeah. Previously it was K over omega, now it's K tilde over omega.
So what happens?
I hope to draw a picture.
No, like,
Yeah.
when we drop the little vector thing over the end of G chart.
Yeah.
What are we doing?
Oh, right. So by this, what really we have done is we chose this to be,
Oh, okay.
yeah. If you choose this, then you get this.
Okay. Yeah.
Yeah. So I should say this plus this implies so the wave part, the oscillatory part is still K, it's that K. It just has a complex expression, that's all. But this time I don't mean complex as in a complex number, just, it has a square root and square root built into it. But all the other features are the same, and lambda equals 2 pi over K. V equals omega over K, because all of these have to be real numbers. And N equals, or V equals C over N. And so if I were to draw this, because this is the wave part, this is an attenuation. So my electric field is going to look like this. Yeah? Because as it goes in the z direction, the amplitude gets decayed. Now, I'm going to mess up B. It's shrink. Yeah, I would try to correct it because I'll make it worse. So B attenuates at the same rate. Let's talk about a little bit about the relative phases of E and B. Again, they're not in phase. So I'm going to write any complex number. Are you done with K's? No. Any complex number can be written as amplitude times e to the I, some complex phase, correct? Chip, have you seen that? Yeah. So this is my magnitude. So a complex number has two parts, the real and the complex part. It can be written this way. Where, I mean, by this I mean, of course, K, uppercase, huh? Gosh. Cosine phi plus I sine phi, the usual Euler form. So if we write it this way, well, of course, by this K, I mean the absolute value of kappa, K tilde, which is, of course, K squared plus kappa squared. So my kappa is this, it's a K with a longer boot. And there's a simple expression we had the expression for K and kappa, so that we don't mistake anything. Here it is. So this is just a lot of algebra. Well, this is the definition. But these are some of the things that you have to verify. There's nothing complicated about it. And phi, as usual, is the arctangent of y over x, or kappa over k. So this is how you would convert any complex number to this Euler form. Using this, we can get the relative phase for E and B. I'm going to write E0 tilde as some real E0 plus E to the I, the delta E, the phase of the electric field. And B, I'm going to write it as B0, I'm going to write it as real B0 times E to the I delta B. That means when I look at this over here, I would get B0 e to the I delta B is equal to K tilde over omega. K e to the I phi over omega E0 e to the I delta E. So there, the phase is off by this factor. So then I can write E, the real part, to be E0 e to the minus K, kappa Z. I want to do real part, so cosine kz minus omega t plus delta E in the x direction. And then B is going to be B0, you know what B0 is, e to the, I'll tell you what B0 is, cosine kz minus omega t plus delta E plus phi in the y hat direction, where E0 over V0, these are real parts, is nothing more than K over omega. I realize I'm just writing this down, but it's just algebra that you have to verify. Let's just quickly take a look to see if this makes sense. You can, first of all, you can see this is how these two are related. So you write the complex number as real in the Euler formula. Yeah? Then the magnitudes, the real part will have to be the real part of this divided by omega. So when you look at, that's the real part, so over omega. And then the phase of the magnetic field differs. Now phi is made up of mu, epsilon, and sigma. Lots of algebra, but that's how the field attenuates. One minute to spare.